So I'm going to speak today about the Koopman operator, geometry, and learning of dynamical systems. And let me first introduce the topic a little bit in the context of sort of history, and then tell you what I'm going to be saying today. So this is the theory session. So I'm going to try to provide a little bit of new theory. So originally these Bernard Koopman, who is here, and then John von Neumann followed right after, tried to reformulate classical mechanics in terms of evolution of observables. Today we know that the reformulation of large swaths of dynamical systems theory is possible to do in that, but I'll speak about that today in some broader terms, and in particular how geometry is recovered. Now, the roots of the approach were inspired by quantum mechanics, and it's interesting that for many years an approach from Koopman operator to the quantum mechanics was not done. Today, that's not true anymore. There are a number of research groups that are actually doing that, and I just participated in a workshop that was supposed originally to be in Germany, that was attempting to connect the classical and quantum mechanics to the Koopman operator. In the last 20 years, we've studied dissipative systems quite a bit and developed data-driven methodologies. Maybe this is the reason of the popularity of the approach today, because it is data-driven. One can get dynamical systems objects from data directly. And the idea is, and this is the elevator pitch, that spectral objects associated with this class of linear infinite dimensional non-self-adjoint operators help unravel the state space geometry and enable model reduction and control. Now, the relationship to data analysis is direct. I also always like to point out this relationship to stochastic process theory. So what am I going to do today? I'm going to introduce something that hopefully is going to sound to you as a new concept, and that's the concept of representation. The key to this is going to be the invariant subspaces of the Koopman operator, but maybe not in the view that you already have, because very often Koopman operator is thought of, hey, any nonlinear system can have a linear infinite dimensional representation. I'm going to turn the table on that a little bit and speak about nonlinear representations and how they connect to the Koopman operator, and what is the relationship. And then I will also define this new concept of the static composition operator for representation of data relationships that are not necessarily dynamic. So perhaps outside of the context of a dynamical systems conference, but hopefully still a little bit interesting. And then I'll give some maybe off-the-cuff remarks on mathematical learning versus human learning and how that all connects to the Koopman operator. My thoughts are mostly from this paper here that is on arXiv, but it will appear in the notice of the American Mathematical Society soon, I think in August. So the history of this is, and every now and then I'll have to do this to figure out what time I'm on. Sorry about that. There we go.
I will also give you a 5 and 1 minute warning.
That's great, because I don't actually see anyone on screens. For some reason, Zoom is set up for me this way. So recall, we have observables on the state space. This is the classical context. We have observables on the state space. The Koopman operator is the composition operator with either a map or a flow. These are the original references. And then in the familiar vector field case, we have x dot is equal to f of x plus possibly some control driven by u. And the generator equation is this. And then we look for eigenfunction equations in this form here. And if we find an eigenfunction, we tend to be pretty happy, because we can reduce the dynamics to dynamics of the eigenfunction itself, understand the geometry of state space. We can project observables on the eigenfunction itself and find what we ended up calling Koopman modes, and so on and so forth. But I'd like to take a step back and a little bit more abstract point of view, where I don't get given perhaps a nice smooth dynamics My dynamics is entirely on some space M. There is an abstract map T from M to M. And then this operator here is defined as a composition on T acting on M. Now, here is the first definition. So I'm going to call a set of functions, a vector set of functions F, and then a map, capital F, a finite dimensional representation, provided that the action of the Koopman operator on this set of functions is the second set of functions, capital F, composed with little f. So if you're wondering why I'm doing this, I'm starting from an abstract M, and I'm applying numerical evaluations on that point in that set, and then I'm porting them forward with this Koopman operator acting on the functions, not necessarily, of course, on the points in the state space, but on the functions, and asking that this relationship here be closed. And so bear with me, and you'll see slowly, hopefully during the talk, how this turns out to be somewhat useful. So an example in which, which I need to immediately use complex functions in this set rather than real functions is rotation of the torus, where if I choose my set of functions to be z1 and z2, where z1 is e to the I theta 1 and z2 is I to the I theta 2, then I have f prime is af. I have a linear representation of the nonlinear dynamics of a rotation around a two-dimensional torus, right? So that's going to be, that's sort of a typical objective in Koopman operator theory, at least in data-driven analysis, to reduce the system to some linear representation. Let me do some more definitions. A representation is going to be called faithful, provided my set of functions f is injective. In other words, it separates the points on my original set. So if m is different than n, then f of m is different from f of n as well. And I can now immediately do a classical Takens theorem in this language. So far I've provided just a little bit of language. And so if I define f tilde as a set of functions that is obtained from taking a single function, single observable f, and time delaying 2m minus 1 times, then I get an embedding, and Takens tells me that for generic pairs of observable and the mapping, the f tilde and f is a faithful, real representation of T. So Takens and Isles as well, on the same side, he have been working with the real representations. So we go a little bit further and say an n-dimensional faithful, remember that means injective, representation is called efficient, provided there is no capital H, such that one of the functions fj in the representation can be obtained as functional, in functional relationship with all the other functions. Think about of x dot is equal to lambda x, where lambda is a constant, and then x squared is kind of useless because it's an additional function, but it depends functionally on x. So it wouldn't be useful to me. So here is a first meaningful proposition, and this relates to taking different observations on the same system. Suppose that you have f capital F and g capital G to be two different but faithful n-dimensional representation. Then there is a bijection H such that F is H of G, and H is a conjugacy of representation. I'm using conjugacy here in a very general, in a very general meaning. I'm not assuming any continuity or smoothness. It is really just this relationship itself. So it is useful to think about reduced representations. If you think about it, if you find a single eigenfunction of the Koopman operator, then that provides you with a reduced representation of a system. There was a talk on Moritz-Wanzig representations, and I remarked in there that if you are projecting to eigenfunctions as your observables, that you don't have, for example, any memory terms. So you have an exact representation of higher dimensional dynamics that is in fact deterministic in that case. So these reduced representations that are not faithful, so they don't separate points on the state space, can be useful. They're additionally related to the notion of factors in ergodic theory. So in that case, we need to equip our state space with a measure mu. And if we have a reduced representation, where the components of f are measure of functions of f, then the dynamical system f prime is capital F of the set of functions is a factor with respect to the measure that is obtained naturally by the pullback from the measure defined on the original space. So in other words, representations give us factors, or alternatively, if you want to be in a continuous category, they give us what are called the semi-conjugacies. So meaning a conjugacy, but to a lower dimensional system. So if our f is a continuous proper surjection, in other words, there are 2 points that map to a single point, and we have a non-faithful representation, then capital F is semi-conjugate to our mapping T. So these are some structural results. We can do the same type of a thing in the continuous time, and in the continuous time, the evolution consists of group transformations, TT, satisfying the group property, and then any such evolution group has a Koopman operator. And now, if we find a representation, that means that it satisfies this property that f of the time evolution is found as capital F acting on lowercase f of m. And you could say that the representation is called ordinary differential representation if it is finite and this vector field exists that is defined as a limit. Now, this again might seem like maybe unnecessary, but actually, if you consider the system, for example, on the Lorentz attractor on a fractal set, you might wonder whether there is a vector field associated with the evolution. And it turns out in this context of representation that you can prove that there is. So Lorentz, of course, is defined on the full 3-dimensional space, but I'm talking about data-driven analysis in which you might have a system literally defined on a fractal set that has an ordinary differential representation. So that's why this definition is proposed here. Okay, so in classical ergodic theory, the notion of partitions is paramount. So for example, you could partition a dynamical system into some collection of invariant sets. In general, a collection of disjoint sets forms a partition if and only if the union over all alpha, in this case, in the complex plane of A alpha is equal to M. That's just the parameterization or indexing of your sets. So a particularly important notion of partitions is a subclass of partitions is those induced by an observable. So partitions induced by an observable satisfy this definition here. They're composed of elements of the set such that each element of the set is the pre-image under some observable, complex observable in general, pre-image under the function f. So there are sets of all points in the space such that when you apply the observable to them, that gives you an alpha, and the product of two partitions is obtained in an obvious manner as the intersection of the sets in each individual partition. And so here is a nice relationship between, mind you, the geometric notion of partitions. Those are sets on the state space, the geometric notion of partitions, and a representation which is, as we saw, an operator theoretic notion. The representation is defined essentially through the action of the Koopman operator on functions. So we say the representation is faithful if and only if the partition CF here is the finest partition pi, meaning partition into individual elements of the set. So that's a nice connectivity between the notion of faithful partitions and this geometric notion of partitions themselves. Okay. So let's now talk about the different types of representation. Let's see that I'm still within time. Okay. Hopefully you can still see my screen, right? Everything is fine?
We just see you.
Right. Let me share. Yeah. Just a second. Okay, a bit of a technical problem, sorry. Should work now. You see it now?
Yes.
All right, thank you. Okay, so let's now go to linear representations. So a finite dimensional representation is a set of functions and these mappings such that this is satisfied. This representation is linear provided this F is a linear mapping. So you immediately find that eigenfunctions provide you with linear representations. Actually, this lambda here is lambda times phi is exactly that linear mapping, and therefore you find an eigenfunction, you find a linear representation, finite dimensional, one dimensional in fact. But you can port that to a little bit more general context and say, hey, why don't I ask the following question? Is there a matrix A and a set of functions F such that UF is AF? So you could call A an eigenmatrix. Now, why is that different? Well, it's different because this notion here, an eigenmatrix, could possibly have generalized eigenvectors, and those would lead to generalized eigenfunctions. So it does make some sense to consider this relationship here as a generalization of the eigenvalue relationship itself. And in the continuous time, you have UTF e to the ATF. So everything ports over. For linear representations, now, using the representation itself and the fact that it's easy to find eigenfunctions of the Koopman operator for linear representations, you can actually find the eigenfunctions of the original system by just inner producting F, which, remember, is a function of M, with Wj, which is, of course, the left eigenvector, one of the left eigenvectors of the matrix A. So you immediately find from linear representations with eigenmatrix A, you will find eigenfunctions in the same way you will find generalized eigenfunctions. In fact, if you have generalized eigenvectors Wj, you find generalized eigenfunctions as well. And of course, eigenfunctions of U form an algebra. If you have two of them, then the product is also an eigenfunction. Now, this is not true for generalized eigenfunctions, but it's true for eigenfunctions. And in that context, if you have an efficient representation using n eigenfunctions, you're going to get many non-efficient representations that can be obtained as products of eigenfunctions. All right, so let's talk a little bit more about the geometry now, using these partitions. If phi is a Koopman eigenfunction of a continuous time system, then the level sets of phi are elements of an invariant partition C phi. So elements, so if you take a partition into individual level sets, that's true for any eigenfunction. We started on this with eigenfunctions for measure preserving systems, but that's true in general. So let me define another new notion. Classically in ergodic theory, we have what is called recurrent invariant partitions. So invariant partitions are those that you take a set and you map it with a mapping into another set. But
Give me a warning.
how much?
5 minutes.
5 minutes. So a non-recurrent partition is basically the one that you start from some set A, and there is a time after which you're not going to be close to A. So in non-dissipative systems, you don't have non-recurrent partitions. In dissipative systems, you have isostable partitions, for example, where the system of these topological circles comes closer and closer to the limit cycle as time goes to infinity, and these partitions are non-recurrent. So from the perspective of ergodic theory, these are new objects. Besides linear representations, we could define nonlinear representations as well. So it starts with space of observables that are constant on joint level sets of F, and observe that that's a linear subspace of the set of all observables. Now we're going to call O to be generated by a finite set of functions if it's the subspace of the full space of observables containing all the functional dependencies on your original set F. And that's, in general, typically, an infinite dimensional space. So the point here is that here is a corollary of these results, that any finite dimensional invariant subspace is spanned by observables in a linear representation of dimension n in a span of generalized eigenfunctions. But you can have a finite dimensional nonlinear representation. In that case, the subspace is generated by F is an invariant subspace, and I should point out, typically infinite dimensional if you're in some standard functional setting. So this leads to the following. There is a proper generalization of the eigenvalue problem for the Koopman operator, and that's in finding a set of functions F and the map, capital F, such that they satisfy UF as the map acting on F themselves. So this problem deserves, I think, a further look. If you just take F to be a linear matrix here, you're going to get our standard linear representations. It's clearly associated with infinite dimensional subspaces of the Koopman operator. And one of the approaches that even Alan Avila himself is pursuing, and Michael Banks, who I think is in this talk as well at UCSB, is use neural networks to approximate both capital F and the set of observables, a little f here. So I would argue that this is an interesting, mathematically interesting problem that reduces to an eigenproblem in the standard case. Now, if we have a control system and nothing much changes, the reason being that it's really a standard dynamical system with a driving system N being the control and having a skew product structure. And so in that case, you have representations. For example, you can have linear representations that have this form. It's a very particular form where you have linear matrices, matrices A and B. And in general, if you have a feedback system, you might have this feedback relationship that couples the two systems. And
This is your final minute now.
Okay, more on this in this Koopman operator in systems and control that Alex Mauro and Yoshi Suzuki and myself did last year. Okay, in my final minute, I'll say that there is a way of defining Koopman-like operators or static composition operators for maps between different spaces. So now we have observables on different spaces. The representation now has a set of functions G on one of these spaces, a set of functions F, capital F is similar. And then it's called faithful, provided again we separate both the input F and the output G. And the pullback, which you can think of as the pseudo-inverse, the pullback composition operator is defined by taking functions on M and composing them, taking functions on n and composing them with t. You can also define the push forward operator, and the two are the inverses, inverses of each other. You also have a spectral characterization of the space of functions that are constant on level sets of t, and in that subspace is orthogonal to the subspace at singular value 0. So again, you can do spectral computations and obtain the geometry of the mapping itself, and you can characterize the projections to that particular subspace using conditional expectations. All right, so numerically, this reduces, if you want to do something like DMD, to something similar to DMD, where X and Y are now two separate streams of data, so the input and the output. You minimize this matrix, and you get this again. And so I will close here by saying the Koopman operator framework has emerged as one of the key elements in trying to learn dynamical systems in general. The take-home points are that linear representations are always associated with generalized eigenfunctions, and they can give you finite dimensional representations even of infinite dimensional, nominally infinite dimensional systems. Nonlinear representations involve a search for infinite dimensional invariant subspecies of the Koopman operator. I would muse on learning a little bit and say what is today called machine learning is a set of powerful techniques in functional approximation. The key issue in these is they're interpolative, have bad extrapolation properties. What we have just defined is an ability to build generative, if reduced, models. And so extrapolation and prediction, as well as self-adaptation, are actually possible. We've done quite a number of, quite some strides in that direction. These functional approximation techniques, like neural networks, can be efficiently used within the Koopman framework, and I'm done. Thank you for your attention.